Hello, everyone. My name is Parinita Rahi. I am a principal PM in the AI frameworks team within Microsoft. And today I'm going to talk about the Azure Container for PyTorch. So the Azure Container for PyTorch is a curated environment or a packaged container that enables easier setup for your deep learning large workloads, specifically curated for PyTorch models. It has been tested within Microsoft across a large set of 1P workloads. So it's pre-tested and pre-validated. And it comes packaged with software and libraries that will help you enable your training times easily, like it'll reduce your training time significantly, as well as also includes some of the open source Microsoft deep learning technologies that can help with training tasks. I'll talk about that a little bit more in the coming slides. So the Azure Container for PyTorch is available in two variants. One is as a curated environment, and another one is a data science virtual machine. So the curated environment is a managed and versioned entity that exists within your workspace, and you can use it to repeatedly perform your training tasks. It is easily managed within Azure, and it's available within the Azure ML SDK, CLI, as well as Studio. And as a DSVM, you can also use it to run a customized VM image with all of these pre-packaged libraries. So what's included within it? It contains up-to-date stack with Ubuntu, Python, PyTorch, and some of the GPU drivers like CUDA and ROCm. Additionally, it has accelerators like the Onyx Runtime cross-platform accelerator that significantly improves training time and supports a variety of operating systems and hardware platforms. ORT can be composed with deep speed, which is another open source accelerator that comes from Microsoft, and that can be used both for training and inferencing tasks. Additionally, it has various other packages for your training workflows, like MSYCL, which is inter-accelerator communication framework, it also includes things like PyTorch Lightning, PySpark, OFIT drivers, etc., which are things that if you're starting an ML training job, you would need. And so what ACPT tries to do is take away the load from the researchers in terms of trying to figure out what are all the various packages that I need to install to get my workflow running, and focus mostly on the research task itself. So it has helped to ease the burden and make it easier setup and repeatable training. Next slide. So we've run the ACPT container across various 1P workloads, and I'll give some examples in the coming slides. But with the Hugging Face models like Roberta Large or GPT-2 and others, we have seen anywhere from 39 to 103% faster training times. So it definitely helps accelerate, specifically when you use it with the inbuilt technologies like Onyx Runtime and Deep Speed combined. So one of the 1P scenarios we had is from Bing. So Bing Ads team runs transformer-based model trainers, which use billions of parameters, and they're enabled for over 130 markets. So training and resource management is a big area of concern for them. And so what ACPT helps do is that it helps reduce the training time. So they see about 1.3x to 2.4x speed up when they tried this container. So, and that helped them work with the limited managed resources, and also scale their workloads and perform them repeatedly over and over again. So the next customer we had was Fashable. Fashable is a small startup, and that uses AI technology to generate original clothing designs, and that helps fashion companies to meet customer demands and get to market faster and reduce clothing waste. And for them, again, given that they're more focused in improving the technology itself, the use of ACPT helps minimize the burden of setup. And additionally, I think they were having some challenges with the dependencies between CUDA and some of their other internal packages, and so ACPT helps make that much, much easier. And so the small team with limited resources can focus more on their GPU workloads and training tasks. Internally also within Microsoft, the Azure Cognitive Services is another user of ACPT. They use state-of-the-art computer vision technologies, and that is run over like hundreds of GPUs. And with ACPT, the team again has to worry less about setup and focus more on the research work, and that significantly improved productivity as well as training resources. So how does PyTorch work on Azure? It supports, at the hardware level, it supports NVIDIA GPUs within Azure ML. So you have the state-of-the-art A100s and V100s available within it. But you can also run it on AMD GPUs like ROCm, etc. And then, as I mentioned earlier, it's available within the Azure ML SDK, Azure ML CLI, and Azure ML Studio, which comes with the Azure Container for PyTorch curated environment, easily integrated. So if you're using any of these, you can leverage the Azure Container for PyTorch, and that has all of the required setup for PyTorch, Python, Ubuntu, and CUDA, and along with Onyx Runtime, DeepSpeed, MSQL, etc. So once you have this setup, it's very easy for you to then run some simple scripts and set up your compute targets to use models for like transformers or GPT-3, and then convert it into Onyx format so you can deploy it on any hardware accelerator of your choice. Let me show you how to do that in the next slide. So, this is a quick demo showing you how you can use ACPT. Is it playing? Sorry about that. So today I'm going to show you how you can use your Azure Container for PyTorch for a Distilbert fine-tuning demo. In here, we will use a Hugging Face BERT transformer model, and then show you how you can do that by first creating a curated environment within Azure ML, and then creating a custom environment, because for the transformer task we might need additional dependencies. And once you've created the custom environment, then how do you use ACPT for your training task? And then once we have a trained model, how can we'll use a DeepSpeed and Onyx Runtime to accelerate training times, and then show you how to deploy it on Azure ML and inference using Onyx Runtime. So for this demo, we're using the Hugging Face BERT model, which is fine-tuned with the squad dataset. This takes in a question-answer scenario. So you provide a context and a question, and the model will tokenize and encode the questions and the context, and feeds the input into the transformer model, and then generates the answer by producing the most likely start and end tokens. So this is the example that we're going to show you with ACPT. Some of the demo resources, you would need an Azure subscription, you would need access to the Azure ML workspace, and you would need Azure portal access. Some of the architecture and terms are described in the demo resources, so you can take a look at it later. There is a file source code wherein we have a dsconfig01 file, which is JSON file, which is required to enable deep speed within your training workflow, and a fine-tuned Python source code. That source code here helps show you, you can enable parameters to implement ORT or deep speed within your fine-tuning task. And then for knowing more about this Hugging Face transformer model, there is a link in the source code that you can take a look at, which tells you the details of the transformer model itself. And then for the datasets library, as I mentioned earlier, it uses the squad dataset. So you can take the, if you specify the ORT parameter, then it calls the ORT module and converts it into the Onyx format for training. And then if you specify the deep speed parameter, then it will invoke the deep speed state 0 for optimizing your training task. So now I'll show you how to create curated and custom environments. So if you come to the Azure ML Learning Studio, you have an option of curated environments. If you search for ACPT, it will show you all of the existing versions of the Azure Container for PyTorch that are available. So in here you will see you have PyTorch 1.12 with Python 3.8 and CUDA 11.6 GPU that's packaged within the container. And this is the Docker image and some additional Azure ML dependencies that come with it. So this is the curated environment. Now, if for your task, and like for our task here, we would need additional dependencies, you can also create a custom environment. So I'll give it an environment name. So in here, I've given it a name for the environment that I want to create. And you can give some description, and then you select start from existing environment, and we will select the ACPT environment that we showed you earlier. So this shows you the previous environment setup that comes with ACPT. You can use it as is, but for our task, we need additional dependencies like the transformers and datasets. So I will go ahead and add that. So I've added transformers, accelerator, and datasets into the base image that I got from ACPT. And once I have that, then I can hit create, and that will help generate a new curated environment, which is based off of ACPT. These are tags. If you want to specify them additionally, you can help provide that. And so once I hit create, that custom environment can be created using ACPT. So now that I have a custom environment that is generated, I will use this now for my training workflow. So to do that, I come to Azure ML Studio, hit create job, and then it asks me to select a compute type. So you can either select a compute cluster or you can select automatic compute and what type of virtual machine you want to use. It gives you a couple of options that you can select from that are available in your workspace. And then within the environment, you can, if you're running a basic training workflow, you can use the PyTorch 1.121 ACPT image. But for our task, given we have already created a custom environment, I will go ahead and use the custom environment that was created. And then I need to specify some job settings like the training job name, an experiment name, and then the fine-tune.py code that I had shown you earlier, we need to upload all of the source code. So I'll upload the code from a local directory. And so I have the fine-tune.py and the JSON file that I showed earlier. And to start the job, I just need to give a simple Python command, which is python fine-tune.py. So in this demo, we will show you both what the improvement in training time is with deep speed and ORT enabled and without. So I'll run one run of this command without the deep speed and ORT parameters and another with deep speed and ORT parameters. And basically we specify that. And hit next. It also asks you for a distribution type, so you'll specify PyTorch, it'll ask you for process count. You can specify 4 or 8 based on your workload needs. You can also add tags so that this training job is searchable for you later on if you want to repeat or retrain within the same job. And then you hit create. So there are 2 versions. One when we did not specify fine-tuned deep speed and ORT, and we see the total train time is 8,440 seconds, which is around 2 hours, 40 minutes. And another version where we had specified fine-tune.py with the deep speed and ORT function. And so for that, it only took 5,044 seconds, which is 1 hour, 30 minutes. So from 2 hours, 40 minutes, it came down to 1 hour, 30 minutes. That's a huge speed up gain, over 60% gain in your training time. So imagine if you're running large workloads over and over again, how much compute resources you're saving. So next step I'll show you is how to deploy your trained model on Azure ML with Onyx Runtime. So there's the resources that are shared there. You can do it through CLI by installing some of these dependencies. And then once we have it, we'll convert it into Onyx format, and once it's converted into Onyx format, then we'll deploy and run it with, or inference it with Onyx Runtime. So I locally convert my model into the Onyx format just for ease of showing. So it takes, you need to run the model in evaluation mode and then convert from torch.onyx.module. And then I'll show you how you can inference it locally just to make sure that the model works perfectly. So we will run the model locally with this question and some additional context for Dolly Parton. And my question is, what is Dolly Parton's middle name? And it gives me the answer, Rebecca. So we've tested that the model works fine locally. So now that we have a model that works, let's see how we can deploy it on Azure ML endpoint. So I come to the Azure ML Studio and create a deployment and give it an endpoint name and a description. Once I have a description, I can specify the compute type that I want to use and the authentication type that I want to use. It then asks me to register a model. So we had already created a model and converted it into Onyx format. So I will go ahead and upload the model from my local directory. So I'll upload this transformer model that we had created, and then hit next. And then it'll ask you just for a name, description, and version. So once you have registered a model within Azure ML, you can use it within various endpoint deployments and various tasks. And you can give it a tag to easily find it again. Once the deployment is done, you can then, you need to specify a scoring file. So what scoring file has is basically 2 functions. One is an init function that runs once, wherein you create the tokenizer and you create the Onyx runtime session, and a run function wherein the inference task is performed using Onyx runtime. So this is again another input that will be required to be uploaded within the Azure ML Studio workflow. So I'll go ahead and upload the score.py file that we created. And then you can select the environment type. So we had the custom environment that we had created, which can also be used for inferencing. And then it asks me for VMs. So you can select the VMs available within your workspace that you want to run your inferencing task on. And then specify instance count. Once this is done, it asks you for traffic allocation, and you review the setup and you create your deployment endpoint. So now that you have a model, you have trained it successfully, you have seen how much training time, acceleration and improvement is made. And you've also seen it locally that the model works fine. You've seen how you can register your model. The last step is basically the inferencing task, and so you can do that easily with a command line command wherein you specify your subscription, your resource group, and your workspace name. And so with that, you can test the deployed endpoint very easily on Azure. So hope like the demo itself was useful, and it will tell you how easy it is to run ACPT on Azure, and how simple it makes the task of training and inference for you, so that as a researcher, all you're focused on is the models itself and the technologies that you need to enhance within the model to achieve your end goal. So some of the resources are shared here. So there are blog posts that gives you details about ACPT, so you can access them later. And then the demo resources are also available as the slide. And the last step is there is a form. It will be really helpful if you can take the short survey and provide feedback using this QR code.